Well, thank you very much. So I'm very much pleased by the possibility of working here. And this is really an opportunity for me to actually to present this topic for the first time, I think, and I would say 4 years of that. So, but first starting with a little caveat, okay? So my talk will be definitely about application of mathematics, but mathematics here is rather rudimentary, probably very simple for you. So if I make some detour into mathematics, it will be solely for fixing the terminology and notation. Okay, so there will be nothing special in mathematics. It will be not about mathematics. I remember it was theoretical, so it was like the very beginning of today's sessions. So because what I want to entertain you with is there is something. Yes, easily. Okay, so let me start with goals and means of this. I would say it will be a kind of case study. Okay, so this is an analysis or description analysis, further analysis of some experiment, which was actually of a psychological and neurophysiological nature, and it was somehow invented or constructed by my fellow colleague psychologists, and it is really model here. So this was identification of features of artistic images that influence the perception of art. This is a very rough statement, but you will see what I'm going to talk in the future. You will see what is actually what we are concentrated on. Okay, so what was the experiment? Experiment actually was quite, I would say, sophisticated and involves two real exhibitions, so gallery exhibitions. First one was the exhibition of, I would say, 12 paintings of young, talented artists, real artists. Okay, it was abstract art. You will see immediately how this pictures look like, so this images. And the second exhibition was put, I would say, under the same, I would say, circumstances and some form as the previous one, so in the same gallery, a few weeks after that, and it exhibited 12 images produced by, say, artificial intelligence. I'm not a mathematician, so this is another caveat. Okay, so I'm using such a, I would say, terms which maybe are not very well, I would say, based in mathematics. There are second things science, other things, so that's mathematics. My fellow psychologist, it was not so easy. So forgive me on the simplification. You will see in later transparency. Okay, so this was actually this were produced by neural network. So the first thing that we did in an attempt to measure an aesthetic value of these pictures, or improve the methods of producing artificial art or something like that, but was really to understand viewer reactions. Okay, viewer reactions to this. So this could be somehow encoded as perception risk. Okay, so there is a team, as you see, it was it consisted of psychologists, my friend physicist, who actually was now specializes in all these things connected to concerned with artificial intelligence and mathematics. I'm not a mathematician, but somehow mathematical part was there. Okay, so these are the description of this new exhibition. I'm not going into details, this is not so important. But first was the author, but as I told you, a young talented painter, and okay, so you will see. Okay, so this is this first exhibition, and you can read something about the author and the, I would say, the exhibition itself. Okay, and these are these 12 pictures. Okay, these are these 12 pictures. As you see, they are really somehow dark pictures. So this is this the 3/4 of black was the title of the exhibition, and it was the exhibition was in Toron, in gallery, and lasted for 3 weeks or something like that. And you will see what we did. Okay, and this is this fake exhibition, as we call it. So this was produced. The pictures were produced by this big gun network. Actually, I'm not very good familiar with how it works, but as far as I understand, this big gun was a neural network, or actually a neural network to produce original goal was to produce images which are somehow close to natural images, close to photographs. Okay, but the idea is that you have two competing networks there. Somehow one which produces this out of what it learned and from some random input, and the discriminator which then discriminates whether it really resembles something natural or not. Okay, and it's kind of game between the two. And but if you manipulate this, you can produce can also output in the form of abstract pictures, I would say. So we tried to keep everything in this artificial intelligence flavor. So even the titles and the leaflet describing the exhibition, which was distributed during the exhibition, they were produced by GPT-3 at this moment. Okay, so these are the pictures produced by the gun. Okay, title was also generated by GPT. Okay, so both exhibitions were somehow arranged in the same way. So there was curator of both exhibition, and there was the same gallery room. So the idea was to keep it actually confidential, so that to the viewers will not reveal this information that these pictures were produced by artificial intelligence, and then we but the circumstances of the environment was likely for the previous. That's fine. Okay, so what was the experiment? So experiment was the following. So we invited 60 students of the first year of artistic studies at the Fine Art Academy in Toron to visit this gallery. So there were several groups. Okay, so details are not so important. I will tell you what we investigated. Okay, so they were actually twice. And they had two visits to this gallery, each group, to one or other exhibition. And then, okay, the psychological part was actually consisted of asking them a questionnaire of questions. Okay, after there was a typical psychological, I would say, investigation, you receive the questions immediately, and so this is the second part, but it was also parallel, fortunately, as you will see, by such a neurophysiological experiment, which was simply they were invited to the laboratory after this visit in the gallery, and they were confronted with the same pictures twice during this, and at the same moment, the eye tracking movement, the movement of eyes were tracked by some equipment. And also some EEG check was also performed. About this EEG I will not talk too much, because first the analysis of the data is not yet finished, and the second, this is probably not a good mean to find something interesting. Okay, so. So this is this question about the psychological experiment. So mostly it asks about reactions, about impressions, whether I like it, whether it was exciting, whether it was interesting for me, and so on and so on. And this is okay. So whether, as you see, I was fully focused, lost track of time, had a pleasant experience. Actually, we were not interested, or my friends, psychologists, were not interested in the bare answers to this question, so whether they really like this or not, but rather to compare whether there were differences between these two exhibitions. Okay. And from the psychological point of view, okay, the results were interesting, but to some extent disappointing, or maybe even embarrassing from the point of view of an artist, because actually there were no differences. There were no visible differences. There are some scores of this questions after this questionnaires were filled by these viewers, but okay, so what does it mean? So the artistic impression with the page these pictures on all participants are more or less comparable to this. Okay, so it was in a sense okay. As I told you, from a psychological point of view, it's interesting, but from the point of view, I would say there was before the discussion whether artificial intelligence will make people jobless and so on, especially artists and newspaper people, something like that. So before all that, okay, but certainly the output was disappointing from this point of view. That really you can imitate the real life. But fortunately, as I told you, there was also this neurophysiological experiment, which from my point of view as a, I would say, physicist, it's much more reliable than a psychological experiment, okay, because you have a real data. And this was this eye track. Okay, so the gaze was followed by some measuring apparatus. Okay? And these are three types actually of eye movement. There are more, but what are very important for us are the so-called, you can imagine, there are fixations. So the gaze is maintained on a single location on this image, and there are so-called saccades. Okay, so these are such movements where you go from one fixation to another fixation, roughly speaking. So you scan, in a sense, the picture. Okay? There are also so-called microsaccades, because if you are focusing on something, so nevertheless there are some quivering of eyes. Okay. So then okay. But what was important for us were these two, so this was fixations and saccades. Okay. This is I would say some kind of heat map of the eye movement. So you will see. So it means that the colors correspond to the time of fixation at this point. Okay, roughly. Okay. So you see that this. So you see that they gaze on this pictures for a very short time, so several seconds. Okay, but this you clearly see that the focus was concentrated on some particular points. An exemplary picture, actually from the real exhibition, but we have it for all paints. Okay, and to see. So you give the average amplitude of saccades is rather different or significantly different for this real pictures and for this fake pictures. And to some extent, you can say, okay, so what does it mean? So this is the idea. So we speculated that it's because if you are confronted with a picture, you look for some information. Okay, it could be some hidden, some unconscious information which is somehow transferred to you, but you try to find something in the pictures. Okay, so if this amplitude of saccades is large, so it means that you look, it's harder to find something. Okay, and this was the case of the fake pictures, and this is somehow also partial confirmation of this hypothesis of assumption, okay? because when they look at the same picture second time, so in this real pictures, so real arts, they were not so they didn't look any longer for anything interesting, whereas they repeat the research also after the second during the second observation. Okay, so now we want to say why it's so. So what is this information which we are? So my hypothesis was that so there must be this was something very simple. So these are abstract pictures. So you do not look for any information concerning whether this is a nice view of the mountains or some beautiful flowers, something like that. But there are some rudimentary, very elementary structures which are in this picture. So I would say for my fellow psychologists, I said geometry, but for me it's topological properties of this pictures. So one of the most important things which I learned when reading about topological data analysis is the concept of persistence. So it means that you usually look, for example, at the picture with different level of resolution, spatial resolution. It can also be a different, I would say, sensitivity to the shape or to the intensity of the color. I will come back to this. But let's say that it is this is with different resolution. Okay, so here is actually the idea of this persistence. Explain on a very simple example. So you have a bunch of points, and then you can resolve them actually as individual parts. You can, with this lower resolution, you see actually the structure which is whole inside, and with even lower resolution, even this whole vanishes. So there are some topological properties which appear at some level of resolution. For example, here you have 5 disconnected parts. Here you have one connected part with a hole inside, and here you have one connected part without any holes inside. So here is a topological somehow features of this pattern. And then they appear at some level of resolution and then disappear. So they're born and dead at some stages. And the idea is that more persistent structures, so with larger this interval when they survive, are more important for this. Okay, so this is return to the mathematics, which is as I said rudimentary and probably not for everybody. So, but this is the part which I always wanted to explain to my fellows, the physicists and psychologists. So these are simply this part of topology which is important for us here is homology. Okay, so this is a familiar concept from simplicial homology theory. So you have a set of points, and if they are finally independent, so you call the complex hull of them a simplex, and then the simplex has spaces which are simply the complex hulls of the subsets of this simplex. You can orient them, so by saying that this particular order of the vertices has an orientation 1, and if you permute the vertices, depending on the sign of the permutation, you have two orientation of the simplex. And the simplicial complex is a collection of simplices which are so nicely grouped, yes. So the faces are also parts of the simplicial complex that if they the two simplices intersect, so the common face must be also part of it. Okay? And then you constrain formal chains of them, so you obtain such a module over integers or Hillian group if you prefer, and then there's boundary operator, which you can which has this property that boundary of the boundary is equal to 0, and then you upon that you can construct cycles and boundaries as usual, and then because this simplicial complex is three abelian group and these are subgroups. Moreover, because of that, one is the subgroup of the another. So sorry for the mistake here. So this is the K homology group, and the Betty number is the rank of this group. Okay, if you stay in this module picture, so this is a basis. Okay, so as everybody knows, so the beta 0 is the number of connected components, and beta 1 is number of holes, and this is the, I would say, my favorite example on which I explain my colleagues what it is for. So how to distinguish this hollow triangle from a solid one. So you calculate this Betti numbers, and you see that this is indeed, it consists of one piece and have one hole. This consists of one piece and 0 holes. Okay. Okay. So now if you have this image consisting of the array of pixels, say, especially when you look this on the screen, and then you can first something which is important here. So instead of simplicial homology, we actually use the cubical homology because this is very well adapted to the goals we are for. So namely that this elementary squares in this cubical homology so represent our pixels, okay? And then out of this, of an array, of the rectangular array of this pixels, we construct our image, okay? So our image is constructed actually. Okay, so this is natural to use this kind of homology. So the complexes are such a cubical sets. It means that they are consist of this element, this integer, unit squares means integer coordinates of vertices, and then maybe segments and points. Okay, and also nicely grouped in the sense that the face is also a member of this cubical set. Okay, so and this is was already told during Professor Mrozek's talk about how to represent actually this topological properties, and this is the idea. This is the pictures which I made myself, but borrow from some paper of Pavel, I think. So this is let's assume that we are looking of this picture. Let's say that this is only in shade of gray, and then we have an apparatus or our eye, which must be excited by particular intensity in the sense physical intensity. So if it is bright, so a mixture of gray is low, then it is visible, and if it's too gray is this pixel, it is not seen, but we can change the sensitivity. So at the beginning, our say device sees only this which have a low shade of gray, and then it starts to see also this pixel, and then this pixel, and this pixel. So you see that it changes from the I would say structure which consists of two pieces with two holes. These are these bright squares. Then one hole is filled. Then it becomes simply connected, and then everything is seen, so this becomes a structure without holes. Okay, the first idea how to represent this is by the no, I have it somewhere else. Okay, by the so-called barcodes. So these are the segments with the length, which is simply the difference between the value of this filtering parameters when it dies and when it bonds. Okay, so these are the two barcodes for this counting our holes. Okay, this one and this one. So this is between 0, 1 and 0, 3 and 0, 1 and 0, 5. These are this which counts the number of connected elements. Okay, so this is one representation. The second representation is so-called persistent diagram, which means that you put on this diagram the points with the coordinates b and t. Okay, and the third one is which is so-called persistent landscape, and which is I would say a simple transformation. It's easier to explain than to write the formula. Okay, so you simply rotate it by 45 degrees, and you draw such pyramids. Okay, so these are triangles with the vertices at this point. Okay, and so this is so-called persistent diagram. Okay, so this is the summary of this. Okay, so this I was supposed to see the other one. Okay, so but okay, so this is what we actually did for all our pictures, and this is the exemplary comparison of two exemplary images from the real exhibition and this fair. Okay, so these are barcodes. Okay, and these are in one and in 0 and 1 dimension. Okay, and these are this length. Okay, so this pyramids. This pyramids is where superimposed obviously one another, and there is a third one which is called Betty curve. I will not explain it here. This is not so important, but this is easy because it's how to count the number of these structures at each point. Okay, of each value of this part. So I would say, okay, the difference is visible. And you can, I have also the pictures for all 12 pictures from the real exhibition and the second one. And this difference in these patterns, quite visible here and here, is maintained through both exhibitions. Okay, so you see that it's really I would say this in a sense one can say that this topology of this homology of these pictures from the big gun production is poorer in a sense. Okay, so the persistence is lower, and okay, this is also okay. So I didn't mention this, but obviously, and I will return to this in a moment. Color space, in a sense, is not one-dimensional. So actually, what we did from each of this image, we obtained a grayscale equivalent, not equivalent, like a grayscale form, okay? And this was for this grayscale form, but you can use the color chart, okay? So you can do it in red, in green, and blue, and these are very similar, which is obvious because usually there are mixed the paints which are used by an artist. There are some mixtures of many hues, I would say, or colors. Okay, so this is not the use pure green or pure blue or pure red. So it means that there are probably equal admixture of each of these colors. Okay, and this is for big gun. It does not end up. Okay, and this is something where we see this very clearly. Okay, so this is the average landscape. So this parameter is averaged over 12 pictures in both in both exhibitions. Okay, and I would say that this is clear that there are differences. Okay. There are differences. Okay. So obviously we are obliged to compare this with some other measures of whatever is important for the visual perception. There are many of them. I would say, I don't know, tens of them, which were produced in history to somehow assess this. Usually, what they say, aesthetic value, what they mean that somehow even usually the authors of these other measures usually were not involved in investigating abstract pictures, but rather I would say realistic paintings, okay? With masters or something like that. And the idea was that somehow these features which they want to measure with these measures are similar to the measures which are relevant for real life or real world photographs, okay? So that's a useful comparison. So there are several of them. So let me give you the overview how they are constructed usually. So you have this rectangular grid of pixels with this grid coordinates x and y, and you have some kind of feature description. We got concrete in the moment, so which simply maps this feature into integers. Okay, these are I would say intensity of gray, for example, or intensity of green, blue, or something like that. Okay, so this is also discrete because there are finite resolution of our eyes or measuring apparatus, and you perform standard histograms with beams at each point, counting the number of this. Counting the number of the values of the f at this point. Okay, so you normalize this, and you this over a whole picture. Okay, so you calculate this. So you simply make a histogram of the values of the page through this whole image, okay? So then you normalize H to a probability distribution, and you can do whatever you want with this probability distribution. For example, you can calculate Shannon entropy, which somehow counts the uniformity, okay? How the uniformity of this distribution is usually with entropy, okay? So let me, okay, so we can refine this, and the refinements actually usually take into account the fact that the color space is a three-dimensional space, actually. This is not RGB space, so red, green, blue, because this RGB is actually two-dimensional, because they are two lines. But so the usual, so color, you can say that it is this three-dimensional space, but color can be described by hue, saturation, and value. So hue is something which, for physicists, is in the frequency of the electromagnetic wave. Okay, this is which is hue, which we usually call color: red, blue, green. There is the saturation, and saturation is more or less the admixture of gray, or more, I would say, exactly speaking, is the proportion between this color and the complementary color of this wheel, which is this hue wheel. Okay, and there is something which is called value, which also in physical terms can be can be described by something which is called luminance, and this is simply a mixture of white and black, so whether it's dark color or light color. Okay, so-called shades and tints. Okay, so you have here dark blue and here light. Okay, and these are the coordinates which are in this LAD color space. Okay, so then you can do the following. You can use this information, and exemplary information of this is you first construct something which is called gradient image. So you have this luminance, this A and B. Okay, so this is the proportion between red and green and blue and yellow, and then you can discrete gradients of that. You take maximum of that, and then you simply, this is now your feature descriptor. So to each point you have something like this. So this is an example of how it works. And then you define something which is called complexity. One of the measures is the complexity of the picture proposed by these authors here. And this is simply the mean value of this G. So it is the ideology behind this is very simple. The more changes, more complicated image. Okay? Apparently, this very simple measure is quite, I would say, discriminative. Okay, there is something which is called anisotropy. So, in addition to an intensity itself, or to this gradient of intensity or intensities, you also take into account the direction of this gradient by simply also making a histogram of the possible values of the direction. So also discretize or put it to several bits in the histogram. You make the cumulative histogram out of the three angles, okay, at each point, and then you cumulate this histogram over the whole picture, maybe with weights which are proportional to this actual gradient or intensity of the gradient. Okay, so, and this is this histogram. And then anisotropy was defined by these authors as a simply standard deviation from the mean, okay, of this for this histogram, which is normalized probability distribution. Okay, so so the idea behind was that for an image this is isotropic, so dominated by lines approximately in the same direction, we expect a small variance of the distribution of gradient directions. Okay, and then there is something which is called self-similarity, and the idea is to confront the picture with parts. Okay, so divide the image into sub-images and to make appropriate histograms. So the same histogram you make for the whole picture and then for the parts, and then there is an idea how to compare two histograms. Very simple, and self-similarity is defined as the median of this measured between, say, two levels of this two levels of this division. The whole picture and some division into 16 parts. Okay, so okay, so you know why it is called self-similarity. Okay? So which has also some connection to fractal image and so on. And there is something which is also very simple in a sense that connected, also connected to this idea of representing by a single function of two variables. And this is very simple. So you perform a two-dimensional discrete Fourier transform of that. You somehow average this over rotations, and then you plot this amplitude against logarithmic state, this amplitude of this Fourier transform against the frequency. And then there's a claim that for different actually kind of pictures, you have different inclinations of the slopes of this Fourier transform, and they are tiny, I would say, but visible. Okay. So we can apply it to our pictures to exhibitions and say how it works. Okay. So this is and this to have a single, I would say, characteristic, single digit and a single number characteristic of our collections of pictures. So we choose the summarized area under this landscapes in dimension 0 and dimension 1. And I would say, so these are our results, okay? So you see that so it is written somehow says distribution of this, so this boxes contain half of the cases, okay, out of 12. So from the first to the third quartile. Okay, so you see that both these areas are really differentiate this two exhibition. This is artist, this is begun. Whereas others make it rather poorly, except this complexity I told you, which also somehow indicates that these pictures which were constructed by Gunn were less complicated. Okay. On the other hand, to discriminate is hard because there are also many which are not so complicated in the real artist production. And there is another one which I didn't expect because it's a small, but the idea is also the same. So you look for line structures in this pictures. This is made by so-called Gabor filter, which is somehow sensitive to the lines, so it means the borders between the areas of different shape and the directions of this, and then you correlate this direction. So from one of such points, at one of such points with all others, you make a histogram and so on, so on. Okay. So the conclusion is, and I'm finishing, the conclusion is that really it is so, I would say, so it confirmed our initial hypothesis that there are some geometric or topological information which we try to see in the pictures, even unconsciously, and this are well characterized by this topological structures which can be discovered using this persistent homology. At the very end, there is something which is okay. Maybe say the next one. Okay, so this is such a nonsense diagram which correlates area and dimension of this total area under the landscape in dimension 0 and in dimension 1. Okay, for different things. So this we don't net, so that's really randomly produced by this guy. Okay, and these are for the real artist usually. Okay, and okay, so this is not a mathematical statement, but rather an experimental physicist statement. So these real pictures tend to somehow follow a straight line. Okay. So this is my section. Whether this random this would deviate from the also this big bang productions. They are they somehow try to follow the straight line. Okay, with some except this is also Rothko here. But you remember Rothko is if you remember the Rothko's production has squares which are rectangles of different colors on the other. So even hard we call them complicated. Okay? So they're also deviating from them. But otherwise the production somehow we don't know why. So this is a simple, I would say, experimental physics observation. Thank you very much.
Very much.